Hi viewers, welcome. In this video we will see about source free RL circuit in first order circuits. In this, two elements are considered, that is, one is inductor and another one is resistor. Both are connected in parallel and no source is connected to the circuit, and for the incoming current to this circuit is 0. The amount of energy stored by the inductor initially is of Li square, and the resistor is a non-storage element, so it will not store any energy and it will only dissipate. And in this chapter we will see what is the response of the, or we can say the natural response of the RL circuit, because the source is not connected to this circuit. The amount of current flowing through the inductor is I of t, and the most advantage of this inductor is that it will not permit the instantaneous change of current. Henceforth we are using that property as the amount of current flowing through the inductor is equal to I naught. Okay, now we are going to apply the KVL into this loop. For that we will draw the loop direction, and this loop direction as per KVL, the direction of loop initially meets the positive potential of VR, so we will write VR, and the next the loop direction meets the positive potential of VL, so we will write plus VL, which is equal to 0. By definition we know that VR is equal to I into R plus VL is equal to L into DI by dt, which is equal to 0. Now we are much interesting about the first order values of current I, so we will bring the values of current to the first derivative of currents to the one side and rest of the values to the right hand side of this equation. For simplification purpose we will multiply dt by L into I on both sides. The equation will become I R into dt by L into I plus L into di by dt into dt by Li, which is equal to 0. Further simplification, the term I will get cancelled out. In this dt will cancel out, L and L will be get cancelled out. The remaining values are, yeah, in this di by I. So di by I is equal to, we will transfer this term, that is R by L into dt, to the right hand side of this equation. The value will be R by L into dt. Now we are much interesting about the value of I. We will do the integration on both the sides. When we do the integration on both the sides, the limits will be I0 to I of t, and here 0 to t. When we do the integration of di by I, will become natural logarithm of I with the limits of I0 and I of t, which is equal to, and in the right hand side of this equation is negative R by L into dt, which in this negative R by L is the constant, so we will take out from the integral part, and the remaining is integration of dt, and that will be t. On further simplification we will apply the limits into this equation, so the equation will become natural logarithm of I of t minus natural logarithm of I0 is equal to minus R by L into t. Now we know that log of m minus log of n is equal to log of m by n, so we will write in this form. So ln natural logarithm of I of t by I0, which is equal to negative R by L into t. Now we know that natural logarithm of x is equal to y. That time we can transfer this form to e to the power of y is equal to x. So we are going to apply this method into this equation. In this, natural logarithm of x term is this and y term is this. So we will apply the above method. So when we applying the above method, e to the power of y value is minus R by L into t is equal to e to the power of y is equal to x is equal to I of t by I naught. Now this is the value. On further simplification, to find out the natural response of this circuit, we will transfer the I naught term to the left hand side of this equation. So the equation will become I of t is equal to I naught into e to the power of minus r by L into t. So this is the natural response of this RL circuit with source free, and the natural response of this circuit is exponentially decaying. This can be interpreted from the equation, that is I of t is equal to I naught into e to the power of minus r by L into t. We know that the response of the RL circuit with source free is I of t is equal to I naught into e to the power of minus r by L into t. Now we will take that time constant is equal to L by R. That time the equation will be I of t is equal to I naught into e to the power of negative t by tau. This will be the response of this equation. If we are applying when t is equal to one time constant, that time the equation response will be when t is equal to tau, that is time is equal to one time constant. That time the response will be I of t is equal to I naught into e to the power of minus tau by tau, which is equal to I naught into e to the power of minus 1, which is equal to 0.3679 times of initial current. That means the amount of current will be decaying from its unity value to the 0.3679 times of I naught, that is initial current, when time is equal to one time constant. This we will see in the graph after plotting the graph. So when we plotting the graph between I of t and t, the curve is exponentially dropping from t is equal to 0 to t is equal to infinity, and at this time when the time is equal to one time constant, and here the time unit of time constant is also in seconds. When time is equal to time t is equal to one time constant, that time the response is decaying up to 0.368 times of initial value of current, and it is showing in the graph. Now if I want to find out the approximative value of the one time constant in the graph, we need to draw a tangent at t equal to 0, and it will approximately intersect the tangent into the time axis at one time constant value. Now at 5 time constant, approximately the response is reaching to its 1% of its initial value. So in that stage, at 5 times of time at 5 time constant, the response is reaching to its steady state value. Next, we will prove that the amount of energy stored in the inductor initially has been completely dissipated by the resistor over a time period. For that, the initial energy stored by the inductor, that is inductor stored energy initially 0, indicates that the initial condition is equal to half L I naught square. Now we know that the amount of energy dissipated by the resistor, we can write WR into, with respect to time, is equal to integration over 0 to t time period, power dissipated by the resistor into time. Now we need to find out the value of PR. So PR, we need to find out the value of PR. So PR is equal to, that is power is equal to voltage into current, and we know that V is equal to I into R. I in this equation is I naught into e to the power of minus t by tau into R, and I is equal to, we know I is equal to I naught into e to the power of minus t by tau. We will multiply and we will find out the value of PR. When we multiplying, the value will be I naught into e to the power of minus t by tau into R into I naught into e to the power of minus t by tau. Now when we multiplying this, on simplifying this equation, we will get I naught square into e to the power of minus t by tau into e to the power of minus t by tau will be minus 2t by tau into r. This is the value of PR. Now we will do the integration after applying this equation into this part. So the equation will become power dissipated by the resistor over a time period t is equal to integration of Pr into dt over a time period of 0 to t, and Pr value is I naught square into e to the power of minus 2t by tau into r into dt. Now in this, the I naught square into r is the constant, so we will take out from the integral, so the value will be I naught square into r, and the remaining is e to the power of minus 2t by tau. We know that e to the integration of e to the power of ax is equal to 1 by a into e to the power of ax is the formula. In this, a is minus 2 by tau, so we will apply it here. So when we applying the value here is when a is equal to minus 2 by tau, so minus 2 by tau, and the remaining is e to the power of ax as it is to be right here. So e to the power of minus 2t by tau with the time period of 0 to t. On further simplification of the above equation, we can take out the term minus 2 by tau to outside, so the equation will become I naught square into r into tau by negative 2 into e to the power of, when we applying the upper limit t to the in place of t, so the term will become as it is negative 2t by tau minus, when we applying the 0 to this above term, that is e to the power of minus 2 into 0 by tau will become e to the power of 0, and we know that e to the power of 0 is equal to 1. On next step, we will multiply the term, that is negative I naught square into r into tau by 2 to the internal values. So and we will apply the value of tau is equal to L by r, that is when tau is equal to L by r, we will apply these values into this equation. So we will get of I naught square into r into L by r into e to the power of correction into 1 minus e to the power of minus 2t by tau. Now on further simplification, we will get of this r term will get cancelled out, so the remaining is L I naught square into 1 minus e to the power of minus 2t by tau. So this is the amount of energy dissipated by the resistor over a time period t. Next, we will prove that the amount of energy dissipated by the resistor is equal to amount of energy stored in the inductor. So we will rewrite the equation once again, which is equal to half L I naught square into 1 minus e to the power of minus 2t by tau. Now when time t is equal to infinity, that time the equation will become the amount of energy dissipated by the resistor is equal to, at time infinity, is equal to half L I naught square into 1 minus e to the power of infinity, or we can say e to the power of minus 2 times of infinity by tau. We can write that we know that e to the power of infinity is equal to 0, so the equation will become half L I naught square into 1 minus 0, which is equal to half L I naught square. This is the amount of energy dissipated by the resistor over a time period of infinity, which is equal to initial inductor stored energy. Initially stored energy in inductor. Now we have proved. Next, if you have any doubts, please write it on the comment box. I will reply. If you like this video, kindly hit the like button below this video. If you have not subscribed my channel, kindly subscribe it. Thank you so much.